In this video, we will be explaining some of the prominent interpretations of the quantum world as well as continuing on with another paradox.
First, we will start by describing some of the main interpretations to explain the quantum world.
The Copenhagen interpretation was mostly directed by Niels Bohr and Werner Heisenberg. This is currently the most widely accepted of interpretations despite it presenting a quite abstract idea.
In this interpretation, physical reality has neither waves nor particles. The wave function is a tool for calculation of probabilities. While the particle travels, waves and particles are illusions from our everyday experience. The microscopic world is not as the macroscopic world. All we can know is what we measure. Therefore, there are no wave-particle duality paradoxes.
The many-world interpretation says that when the particle has a choice, the universe splits up one per choice. In the double-slit experiment, when the particle is faced with the choice of slits, it takes slit 1 in one universe and slit 2 in another. Interference occurs because both slits are activated, suggesting some type of interaction among universes.
The de Broglie-Bohm interpretation presents a solution to the particle-wave duality paradoxes. Also known as Bohmian mechanics, as well as pilot wave theory, the mechanism is simply that the particle and wave are both real physical objects at all times.
One of the most prominent scientists working on this field is Professor Sheldon Goldstein at Rutgers University. A link to his website is provided in the description to this video.
Pilot wave theory is shown well in the dual-slit experiment. Here, the wave component of the photon travels just as before. Now, however, a particle rides along this wave. When it gets to the first wall, it will enter one of the two slits. From there, it will simply ride along one of the paths of constructive interference that has been created by the wave component. The waves are what create the interference pattern. The particle merely travels along one of these paths.
For John Wheeler's Gedanken delayed choice experiment, the wave will travel along both paths. At the first beam splitter, the wave splits at the fork of the road. The particle only goes along one of these waves. This wave deflects off a mirror and it hits the detector at the end. The other wave makes it to the other detector, but the wave intensity is not what is being detected, therefore no click.
When the second beam splitter is turned on, nothing changes. The waves still split at the first beam splitter and head down both paths to the second. This split in the waves is what creates the constructive interference at the second beam splitter. We may not know the path of the particle, but is not necessary as the waves are what allow the photon through. The particle simply rides along one path and gets to the detector because of the wave interference.
Where Bohmian mechanics falls short is through its guiding equation. The conservation laws are not necessarily followed in this interpretation. This is a major problem as we have no evidence that the conservation laws are ever violated. In addition, in Bohmian mechanics, the position of a particle changes according to an equation of motion known as the guiding equation. For instance, for a non-relativistic particle of mass m without spin, the guiding equation is shown here. In this equation, x is the particle coordinate, psi is the wave function, t is time, and the last symbol means the imaginary part of the gradient of the wave function divided by the wave function itself. Therefore, Bohmian mechanics is a fully deterministic theory of particles in motion, but a motion of profoundly non-classical, non-Newtonian sort.
As an example, we consider the case of a particle in a box. The wave function for the particle in a box has only a real component and no imaginary part. Thus, according to the equation above, the right-hand side is 0. Thus, the particle in a box is at rest no matter what energy it has. A similar thing happens to the electron in the ground state of hydrogen. According to this theory, the electron is just sitting somewhere. In our view, the situation is not reasonable.
We now transition to a new paradox to be answered. Consider entangled photons A and B emitted in opposite direction. To express angular momentum conservation and the indistinguishability of photons, we write the state of two photons in Dirac notation. Here, the first term represents the amplitude related to the probability that photon B has vertical linear polarization VB and photon A has horizontal linear polarization HA. The second term has a similar interpretation. According to this equation, the two photons cannot have the same polarization even if their polarization is measured with respect to an arbitrary angle of polarization.
Suppose experiments were conducted in Lab 1 and Lab 2, which are so far from each other that communication by light among researchers in Lab 1 and Lab 2 would take significant time.
Suppose entangled photons A and B are produced at the midpoint between the labs. Eventually, photon A arrives at Lab 1 and photon B arrives at Lab 2. A researcher in Lab 1 measures the polarization of photon A and finds it to be horizontal. Then, according to conservation of angular momentum, the researcher in Lab 2 will, for sure, find that the polarization of photon B is vertical.
The experiment is repeated many times at arbitrary polarization settings, and the results always agree with the conservation of angular momentum. We note that photon B needs to know the polarization of photon A to produce results that agree with the conservation of angular momentum. The question here is, how does photon B know the result of the measurement of photon A if no signal at speed of light could transmit this information? It is a mystery in modern physics that this actually happens. This effect was first measured in the 80s by Elaine Aspect. In the literature, his work is known as the violation of Bell's inequalities.
The important thing for us to realize is that nature maintains the conservation of angular momentum even if it requires breaking the speed of light for signaling. The conservation laws are some of the most powerfully preserved facts in nature.